Good morning, everybody. I hope you have now got the recordings. Balaji would have posted all the recordings. So let me, once I finish the lecture on fields, I will give you the text material also. So let me start from where we had stopped off. This we had covered, susceptibility, okay. Can you see the slides? Okay. Yeah. So we had talked about susceptibility. We had also discussed that susceptibility is related to the relative permittivity. And the most important point that I was making when we stopped the class is that when we are looking at the material at a molecular level, we are considering generally what we do is we might need to consider P as a function of X, Y, Z. But once you know what is the distribution of P, which is again, related by these quantities, P vector being related to E and so on and so forth, you should be able to obtain epsilon R. And epsilon R is a macroscopic quantity which can be measured experimentally, and therefore as engineers we are most interested in epsilon R unless we are designing a new material or we expect certain new phenomena. So I will again reiterate this when we are actually doing the modeling in finite elements. Do not remember that P and epsilon R are the manifestation of the same physical process. They are not separate processes. So capacitance, of course, capacitance is, as we have been discussing many times, C is equal to epsilon A by dN and so on and so forth. But all these derivations, all these formulae that you have learned so far correspond to idealized situations. For example, when you say C is equal to epsilon R, A by D, you are talking about an ideal parallel plate capacitor. And when you're talking about ideal parallel plate capacitor, you're thinking of a very idealized situation where you have infinite plates extending in all XYZ directions, and the dielectric in between is such that the electric field inside is exactly uniform. So E can be obtained as V by D. This is true for an ideal situation. This is not true for a practical situation. And therefore, in this course, we are not going to work with idealized situations. We are going to work with a situation where your idealized assumptions do not work. And in that case, we have to go back to what is capacitance. Now, for capacitance, what do you need? You need charge. You need free charge. Please remember this. We are talking about, I have stressed on the difference between free charge and bound charge. When we are measuring capacitance, we are talking about free charge. So there should be two distributions of free charge which are separated by a finite distance, and that distance must be occupied by a dielectric. So you see you have a charge distribution here, which is not at all like the charge distribution on the parallel plate condensers. So you have M1, which is an arbitrary distribution. You have M2, which is an arbitrary distribution. They cannot recombine because they are separated by a dielectric of permittivity epsilon naught. Now, C is equal to Q by V naught. That is what we usually do. Now, in finite element, what will we do? Okay, I'll come to that later. Once I introduce you to just remember that what capacitance is, the quantity of charge, the magnitude of the quantity of charge and the potential difference between the two charge centers. How we will apply that to finite element, I will come to later. But we are going to work with this expression, which is the definition of capacitance and nothing but that. We are not going to work with any idealized formulae. Now, if we want to know how materials behave, we also need to know how the materials behave at the interfaces. Again, I'm not going to go into the derivation of these things. You are already familiar with it. If you have two dielectrics of permittivity epsilon 1 and permittivity epsilon 2, at the interface between the two, what happens to the electric field lines? There will be some, of course, you will have some electric fields here, which is E1. You will have some electric field here, E2, which may or may not be dependent, and they will be represented by some arbitrary field lines. But at the interface, certain conditions need to be satisfied. And what are they? The tangential component of the fields in the first medium must equal the tangential component of the field in the second medium, which means if you consider any electric field E can have a tangential component and a normal component. So what we are doing here is we are only considering the tangential component. And the tangential component of the two fields need not be parallel or perpendicular or whatever. They may be in arbitrary directions, but the tangential components of the fields must be equal. That is one condition which needs to be satisfied at the boundary, is satisfied at the boundary. The second condition is what happens to the normal component. So we've talked about the tangential component. What happens to the normal component? Now the normal component, and this comes from, I will leave it for you to derive it, or you can look up a UG book. You know how it is done. If you consider a pillbox, you will end up with this expression. That is the flux density, the normal component of the flux density in medium 1 and medium 2 differ by the quantity of charge at the interface. That means the charge must be present exactly at the interface. And what kind of charge is this? You must remember and be very careful about this. This is free charge. So we are not talking about any induced bound charges at the boundary. We are only talking about free charges which have been positioned at the interface. So if this rho s is equal to 0, then of course dn1 will be equal to dn2, which means epsilon 1 e1 will be equal to epsilon 2 e2. So this gives you this expression. So this is the condition at the boundary between two dielectrics. Now let us say I replace this with a conductor. What will happen? Any idea? To these expressions, what will happen to the tangential component and what will happen to the normal component of the field and the flux density? If at if this is an interface between a conductor and a dielectric instead of two dielectrics.
In conductor, no electric field will be there. A normal component will be vanishes, and only on tangential component will be there.
If, let us say this is a conductor, sir, conductor material, and let's say I have a charge here, which is not moving away. Would you not have electric field inside the conductor? You would. It is the tangential component which vanishes. So if this is a conductor, then the tangential component of the electric field will vanish. So E tan 1 will be equal to 0. And since E tan 1 is equal to E tan 2, and this is again also obtained from Gaussian applying integration d dot ds is equal to q, you take over these four surfaces and you will get this expression. So in that case, E tan 2 must also be equal to 0, which means that if you have a dielectric, the tangential component of the electric field in the dielectric at a conductor dielectric boundary must be 0. So even E tan 2 becomes equal to 0, even though it's not a conductor, because at the boundary, E tan 1 must be equal to E tan 2, and E tan 1 is equal to 0 because it's a conductor. What happens to the normal component? Normal component will continue to follow this expression, which brings me to the question I asked you in the previous class. I said That's, if you remember, I said that if you take a surface which encompasses the entire electric field, then the surface integral, let me show you. Yeah. Maybe it was not the previous class, but the class before that, doesn't matter. I say that if you consider a volume, if you consider a surface such that the entire electric field is encompassed, so essentially this is at infinity, then this expression goes to 0. And then I asked you, can you think of a surface, a special surface, which is not at infinity, but still this first term goes to 0? I'll give you a hint. This first term has d dot ds. That means dn component is there. So I need a surface where the dn component must be equal to 0. When will that happen? Can you, in the laboratory, can you choose or build a surface such that dn is equal to 0 at every point on the surface?
Ma'am, you asked that is there any possibility of a surface having the finite radius without emitting that field lines are not having outside?
Exactly. See, only if that's what I'm getting at. dn, if this is dn is equal to 0, if you can ensure that dn equal to 0, then this term will go to 0.
Oh, okay,
Yes.
ma'am. QS is a positive QS and encloses a surface of minus QS surface. No electric field lines from the positive QS will
Okay, good. That's good.
Emit to the negative QS, and it
Right.
won't
Wait,
be
wait.
outside.
Yeah, you're right, but that's a theoretical answer. How will you do it? You're right. I want you to do it. I have a, let's do it. Let's put the question like this. I have this box and fill lines are coming out in all directions. I do not want the fill lines to come out. What can I do?
And then negative Q enclose that surface with another
How
minus
will I
QS.
get a negative Q? I can't have plus Q minus Q. These are all, I mean, who brings a charge from somewhere and deposits? And I want that to be everywhere. So how will I do it? What you're saying is correct, but how will I do it? Sandeep, you're in aerospace.
Ma'am, I'm also thinking that negative charge will be present then only.
How will you do it, Baba? तुम लोग तो इंजीनियर हो, करना पड़ेगा ना? Sandeep, when you are sitting in a plane, aren't you afraid that a lightning will strike you?
Sorry, ma'am?
When you are sitting in a flight,
okay,
in the sky,
mm-hmm.
Are you never afraid that lightning will strike you?
Yes.
Does it strike you?
No.
Why not? Lightning has a lot of charge.
Yes. This is going through the body of the plane.
Yeah. It's going through the body. It's not coming to you. Why? How many of you have ever been in a high voltage lab?
Yes, ma'am.
Have you come to my lab? You're in campus right now, right?
Yes, ma'am.
Yes, ma'am, I have visited.
Yeah. I will still not answer this question. I'll leave you to find the answer. Girish, you are in the right direction, but you have to give me a solution, not a theoretical answer.
Ma'am, in the mirror charges, by placing a conductor,
Yes. Be more specific.
specific.
No, you're right. You need to have more confidence, Baba. You have to be more clear about what you're saying. So, what was I saying? I'm talking about a field which is like this. And I'm saying, we all know that as you go to infinity, the field lines will taper off and ultimately will become zero. But that's not what I want. I say that I want a situation where I have a surface at a finite radius and no flux line should go out. I even showed you this box. All I have to do is, I have to coat this box with a metal, which is a perfect conductor.
Okay.
That's what you kind of said, Girish, but you have to say it properly. So when you have a metal conductor, the flux lines will, so you will have induced minus Q here. That's what you were saying, na? You should have minus Q.
Yes,
When
yes,
you
ma'am.
put a metal conductor, what happens? If you have plus Q here,
It is minus.
equal quantity of charge will be distributed such that the summation of that charge density is minus Q. So equal quantity of charge will be uniformly distributed around a sphere. So you have done these problems in class where you have a very nice looking sphere, which is a perfect sphere and which is a perfect metal conductor. And as a result, what will happen is you will induce a minus Q charge, and therefore all these field lines will be terminated, and therefore dn will not be able to go out. Dn will be equal to 0, and E is of course 0. Et is of course 0. So this situation, this can be satisfied if you have a metal conductor, or if you have a conductor surface, and that is exactly what we do in aeroplanes. That is exactly what we do in many other situations. You will find that whenever we have very sensitive instruments, for example, Ramanuj, when we do partial discharge measurements, we need to put the entire setup inside a metal cage, which is called the Faraday cage.
Yes, ma'am.
Yeah. So what you need to do is you need to build a conductor. You need to encompass the, and what is this called? This is called shielding. You would have heard of this term. And Sandeep, if you work in aerospace, you will have to take care to have proper shielding in your aeroplanes. Otherwise, nobody is going to ride them. Right? So where was I? Okay, so that is about the boundary conditions. On top of that, so you have, let's say you have a flux line D1, which is the flux line medium 1 with permittivity epsilon 1, and dn2 at permittivity epsilon 2. So these will have two components. One is the tangential component and the other is the normal component. So you break it up into dn1, dn2 and dt1, dt2. Now we know that dn1 is equal to d1 cos theta 1, where theta 1 is the angle that is subtended by this flux line to the normal. And that must be equal to, since dn1 must be equal to dn2 in the absence of any surface charge, dn1 must be equal to dn2. On top of that, d tan 1 would be equal to d tan 2, which means that d1 sine theta 1 is by d2 sine theta 2 is equal to epsilon 1 by epsilon 2, which gives us the expression tan theta 1 by tan theta 2 is equal to epsilon 1 by epsilon 2. So the angle of incidence of the flux line, and you can think about this as similar to optical refraction. So when you have a flux line entering through a particular medium and reaching an interface between two medium, it will be deviated from its original path and similar to a ray of light, and it will be refracted such that the angle of refraction changes, and the ratio of these two angles that the two flux lines make with the normal at the point of at the boundary, θ1 by θ2, are related to the permittivities of the two medium. Tan θ1 by tan θ2 is equal to epsilon1 by epsilon2. This is something that you know. This is also called the Snell's law for refraction of electric flux lines, because it is absolutely analogous to the law of refraction of light at the interface between two media, right? Now we come to the main story. We have obtained these expressions. Divergence of D is equal to rho. This is your Gauss's law. We also, so this is Gauss's law. Then we have what is called a constitutive relation, which is D is equal to epsilon E. D and E are vectors. Remember, epsilon is in reality a tensor. But in this course, we will confine ourselves to isotropic, homogeneous media, and therefore, for all practical purposes, epsilon will be a scalar quantity. But that is not the whole story. I'll come to that later. Epsilon is actually a complex quantity, but I'll come to that later. So D is equal to epsilon E. And E is related to the potential as E is equal to minus grad phi. Now, if you put these three equations together, you get this expression. Divergence of D is equal to rho. So put D is equal to epsilon E, which gives you divergence of E is equal to rho by epsilon, and E is expressed as minus grad phi. So that gives you del square phi equal to minus rho by epsilon. Which is, what is this? This is something that you're all familiar with. This is Poisson's equation. And in the scenario that rho is equal to 0, you get the expression rho square phi is equal to 0. What is this? This is Laplace's equation. So Laplace's equation is nothing but Poisson's equation in a charge-free space. This del square is an operator which is called the Laplacian operator, and in Cartesian coordinates, this is given by del square del x square plus del square del y square plus del square del z square. For other coordinates, you will have to convert del square and it takes a different form. We will discuss that too. Now, where was I? Okay, so del square phi is equal to rho by epsilon. Now, what is this rho? Epsilon is the permittivity of a medium. So let us imagine that you have a medium, and in this medium you have epsilon. Epsilon can also be a function of x, y, z. What is rho? Rho is charge density. Rho can also be a function of x, y, z. But one important thing is that you need to remember, rho is free charge, because Gauss's law corresponds to free charge, and this free charge is the volume charge. The free charge in the volume. Why am I making this? Why am I stressing on this? Let us take our case of parallel plate capacitor. Parallel plate capacitor, you will have charges here. Now to obtain, okay, what will we get if we solve? This is an equation. This is a differential equation. If I solve this equation, I will get phi, which is my potential. So I will be able to obtain the expression for the potential at every point, and I will get the equipotential. In this case, it's simple. We know that we will get equipotentials. And if we, after getting the potential, if we find E as a function of minus grad phi, I will get the fill lines, right? So basically, by solving Poisson's equation, I am able to map the electrostatic fields in a dielectric. Where is rho present here?
On the plate.
Who is that?
But it is actually, ma'am, that is the surface charge density. That is a volume charge, right?
this Q is not the rho. I will write this in a way that will that will sort of prevent the confusion. What we are doing is del square phi is being solved as a function of xyz, which is equal to rho as a function of xyz divided by epsilon as a function of xyz, which means if I'm trying to find the potential phi at this point xyz, it will be dependent on rho at this point and epsilon at this point, which is not plus q. Plus q is somewhere else. So this is the point that I need to make, that this rho in Poisson's equation is the volume charge density. So if there is some charge here, this is the charge that will contribute to your potential. If there is no charge, will there be no field? So suppose there is no charge, then you will have to obtain the field as del square phi is equal to 0. Okay. What is the role of plus q and minus q then? Doesn't the field change if plus q minus q changes? I mean, we understand that rho is what contributes to the left-hand side, right-hand side. And if you do not have any rho, you solve Laplace's equation with rho equal to 0. And the rho is not determined by the plus q minus q on the capacitor plates. What is the role of plus q minus q in this equation? Will plus q minus q affect your electric field inside the dielectric? See, these are things that all of you know, but I'm just trying to, make you think about it in a more informed way. Tell me, will the field change? Will the field or the potential inside change if plus q minus q changes?
Yes, ma'am.
Yes. So they must find place in this expression somewhere. See, what I'm going to do is I am going to solve this equation. And if this is equal to 0, I'm going to solve this equation. And what will it give me? It will give me potential inside the dielectric, and it will also give me E inside the dielectric. Now we know that the charge on the capacitor plates will change this E and this phi. So that must be accounted for in the equation also. The equation has to take care of the plus q minus q. How do I do that? How does the plus q minus q information enter into this equation? That is the question. Teja?
Yes, ma'am.
Oh, tell me. Where in this equation is the information about plus q and minus q coded? Ramanuj, you've done my previous course.
Yes, ma'am. Ma'am, the volume charge density won't be affected, but this permittivity.
No, I'm not talking about permittivity. I'm talking about plus q minus q on the capacitor plates. Where in this equation does this information appear? Okay. What kind of equation is this?
Differential equation.
What kind of differential equation?
Second order.
Second order.
Is this an ODE? It's a second order partial differential equation. Now, if I want to solve a partial differential equation, I need the equation. Do I need anything more? Can I solve a partial differential equation just with this information, or do you need some more information from me?
Ma'am, we need
Some more information.
What is that information? What are they? What kind of information do you need to solve a PD apart from the PD itself? How will you get a unique solution?
We need, ma'am, initial condition, a boundary condition. Yes.
Yeah, initial conditions can also be a boundary in time, but that is only in time. So we need boundary conditions. And what kind of boundary conditions would you need here? This is phi. You would need to know phi at the capacitor plates. Only then you can solve. So you need the potential on the capacitor plates to obtain a solution for this equation. And what determines the potential on this capacitor plates? If I want to increase the potential, what should I do?
Put more charges.
Put more charge. Now, can you answer my question? How does the charge enter into the equation? As a boundary condition in terms of potential. So what I'm saying is rho refers to free charge in the volume of the dielectric for which we are solving. And the charge, free charge, this is also free charge on capacitor plates determine the boundary conditions of V on the capacitor plates, and the equation is solved subject to these boundary conditions. So when you change the boundary condition, your electric field will change, even though the equation does not change, even though the material does not change. So even if rho does not change, epsilon does not change, potential will change if the boundary conditions change. And the boundary conditions will change if V changes. So this is clear? So if I solve Laplace's or Poisson's equation subject to the specified boundary conditions on the capacitor plates, I will be able to obtain electrostatic field inside the dielectric between the two plates. So now you know that there are various ways of solving for electrostatic fields. You can solve Coulomb's law, you can solve Gauss's law, you can solve Poisson's equation. Now in this course, we are not going to bother about solving Gauss's law or Coulomb's law. You will need to know it for the purpose of the exam, but we are going to concentrate on the equation. And why is that? The reason is to solve Coulomb's law, to apply Coulomb's law or to use Gauss's law, what do you need? You need the charge distribution. You need to know the charge distribution in your material. Do you generally know the charge distribution? You don't. You do not generally know the charge distribution, so that unless for theoretical problems or very simple problems, it is very difficult. It would be impossible for you to apply Coulomb's law or Gauss's law. But what you do know in your electrical circuit, let's say, for example, your capacitor plates, you don't know how much charge is there on the capacitor plates, but you know the potential on the capacitor plates. If you have a power equipment in service, you would not know how much charge is deposited on, let's say, your rotating machine. But what you would know is what is the potential at a point. And therefore, when we want to do electric field solution in real situations, it is the Laplace's or Poisson's equation which we need to solve. So electric field solution using Coulomb's or Gauss's law is possible when the charge distribution is known. In practical electrostatic problems, electrostatic conditions at some boundaries are known. So at some boundaries, you may know the charge. I'll come to that point later. At some points, at some boundaries, you may know the charge. At some boundaries, at other boundaries, you will know the potential. But you will hardly know the charge everywhere. And what we do is we solve this partial differential equation subject to the boundary conditions, and therefore these are called boundary value problems. Right? Any questions so far? So I will make before, I think this must be the last slide. Before I go on, before I stop today, I want to make one point. Now let's say, let us consider this situation where you have rho is equal to 0. Okay. So what you do is you apply the boundary conditions, which means you have V equal to something here, and you have V equal to V1, V equal to V2 here. As a result, you have an electric field inside. This is what? This is an external applied field. In fact, you do not have to even have it here. Suppose you have a large capacitor, or somewhere you have potential, and you have something here. Even this will experience electric field, right? Even if it is not attached to the capacitor plates, but if it is present in an electric field, it will experience an electric field inside the material. And this is the external applied field, where the charge resides outside the material. Now, let us assume that I have removed this external applied field. Is it still possible to experience an electric field inside a dielectric? In the capacitor plates, I have removed this V. So this V is equal to 0, this V equal to 0. And I tell you that still there is an electric field inside. It may not look like this, but there is an electric field inside. Can it be possible?
Yes, ma'am.
How?
Yes, ma'am.
Due to the polarization in the dielectric medium before.
When you do not have an external applied field, the dipoles are aligned in random directions so that their mean dipole moment is 0. Also, as I said, we are only concerned with free charges. We are not concerned with bound charges. Bound charges do not determine the macroscopic field. It may change the local electric field somewhere here, but it will not give you an overall field. So no, that's not the answer, but it's a common mistake, which is why exactly I'm asking you this question. But we can still have electric fields inside the dielectric, even in the absence of an external applied field. How is that possible? There is some electric field. I'm not giving you the nature of the electric field. I don't know what the nature is. It can be some arbitrary nature, but V is equal to 0 both ways. What would I need to have an electric field inside? Doesn't this give you an electric field? V is equal to 0, V equal to 0, but let's say a charge is sitting here. Would not that result in an electric field inside? It will not be like this, it will be like this.
Yes, ma'am.
So if I have a charge distribution, say, instead of having a single charge, let us say I have a charge distribution. I have a charge distribution. That will result in an electric field, which is different from the other applied field. So this electric charge is because of the free charge inside the dielectric, which is rho. So if I have boundary conditions V equal to V1 and V equal to V1, okay, I'll come. So one way to have electric field or potential is by applying the boundary conditions where I have a potential difference applied across the boundary. In the absence of that, if these are both 0, but I have a rho, I have a charge density inside the dielectric that will also result in an electric field. And this electric field I called Poisson field. So what it means is that when you also have V equal to V1 and V equal to V2, and you have rho, you actually have two electric fields. You have an electric field because of the potential difference across the material, which is like this, somewhat like this. And then on top of this, because of a charge distribution, you will have some kind of electric field. I don't know what the nature of that electric field will be. You will have some kind of electric field. So the total electric field inside the dielectric may not be like this. It may be some combination. So basically, your electric field inside a dielectric can be obtained by the superposition of the Laplacian field and the Poisson fields. What is the Laplacian field? Laplacian field is the external applied field that occurs because of a potential difference between the two across the dielectric, which comes from outside. And over that is superimposed a second electric field, which is because of the Poisson charges, which is because of the charge distribution inside a dielectric, because a dielectric can hold charges, and because of the charge inside the dielectric, you will have a Poisson electric field. So when you solve for this equation, subject to certain boundary conditions, when you solve this equation subject to certain boundary conditions, you are actually getting a solution which can be obtained by the superposition of the Laplacian field and the Poisson field. Laplacian field is the external applied field, which can also be obtained by putting del square phi equal to 0. And then there is the Poisson field, which is due to the charge distribution within the dielectric. Is this clear to everybody, this physical concept? We are never ever going to talk about the bound charges, Girish, because we have already accounted for the bound charges. How? By changing the value of permittivity. So whatever bound charges there are have been taken care of when we have taken an epsilon r not equal to 1. So bound charges do not enter into rho. Is this clear? See, these are things that you know, but when you actually apply the finite element method, you will have to be very clear about this distinctions, and that is why I'm spending so much time over this. So this brings me to the end of electric fields, I believe. Let me check. What did I do? Okay, so next class, I will start with a discussion on electrostatic field solution. So we have understood that to plot the electrostatic field inside a dielectric, what I need to do is I need to solve Laplace's or Poisson's equation, depending upon whether you have rho equal to 0 or not. The solution can happen only subject to boundary conditions, and those boundary conditions are in terms of potential across the boundaries of the material. If there is a volume charge density within the material, that will also cause the electrostatic field to further change, because we then have a Laplacian field, and superimposed on that we have a Poisson field. Okay. And we need to solve, when we solve this, we will get the combined field, which is due to both the external applied field and any charges present within the material. In the next class, we will learn how to solve this. Before going on to the finite elements method, I would like to discuss a little bit about the solution of Poisson's equation, so that you see what is the advantage of using finite element method and not analytical solutions. Okay. Any questions? Sachin, you sent me a mail. I did not understand what you wanted me to do. Sachin, are you there? Okay, he's not here. So unless you have any questions, I'll stop the class now. I am assuming that you do understand everything that I'm teaching, but I don't think that will be true once I start talking about the finite element method. Please do ask questions during the class, because after the class is over, if you get confused, you will not understand what is going on in the next class. So I know you people are still far away and you're not familiar with the system, but it is very, very important that you ask questions when I teach. Otherwise, you will get into trouble later, especially in this course. Okay, thank you.